Hello everyone, welcome back to my channel. This is the 7th video of my video series Chemical Bonding, and in today's video we will try to understand the nature of the polar and non-polar molecule. Now, reason why we are studying this particular topic in chemical bonding is that we are trying to understand the nature of the chemical bonds. So majorly we have studied the covalent bond as well as the ionic bond, okay, with the help of the Lewis approach. There are other approaches also, but before we move to those approaches, these topics are very important to understand. Okay, so most of the covalent bond, they are purely not covalent in nature, and same goes for the ionic bonds or the ionic molecule. They are not purely ionic in nature. So that can be explained with the help of the Fezan's rule that we are going to study in the next video. But in today's video, we will try to understand why there are certain covalent bond which has some ionic character. That is why they started showing the polarity. Okay, and this is one of the important topic from the exam point of view as well. So we are going to study some examples as well which can be asked in exam. Okay, so let's just start with the explanation. So to understand what is polarity, first you need to understand the concept where we study the covalent bond between the heteroatomic molecules and the homonuclear molecules. So what is the difference between homonuclear and the heteronuclear? So homonuclear, if you know homonuclear molecule, these are H2, N2, Cl2 and so and so. And hetero, where the two atoms are different, like HCl, HF and so and so. Okay, so in such kind of covalent bond, what happens is, if we talk about, let's say, hydrogen. Okay, so here they form the covalent bond, but what happens is the electron cloud that they share the electron cloud equally. Why? Because they both are equally electronegative. They are going to pull the electron with the same strength. Same goes for this nitrogen and the chlorine molecule. But in case of HCl or maybe in case of HF, if you compare these two, the chlorine has a higher electronegative as compared to hydrogen. Here fluorine has a higher electronegative as compared to hydrogen. So because of what happen is that the chlorine is going to attract the electron cloud more towards itself as compared to hydrogen. Same goes for the HF as well. In this particular case, whichever is the more electronegative, it is going to pull the electron cloud more towards itself. Because of this, what happen is this HCl, in this case, they acquire slightly negative charge, whereas less electronegative atom, it achieve the slightly positive charge. Okay, and there from this point, the dipole moment or the polar nature started to appear, and we represent this with the help of this symbol, an arrow with a tail. So head point towards the more electronegative atom. Same goes for the HF as well in every case, right? So this will achieve a little bit negative charge, this will achieve little bit positive charge, and we can show it like this. Okay, so this is polar molecule, this is also a polar molecule. So whichever has this kind of charge distribution, that will be considered as a polar molecule. But it is possible to have a polar bond, but still overall molecule may not be polar in nature. We will study that with the help of some example. But before that, let's just do some understanding, or so that if you get a numerical, you should be able to solve that as well. What is the formula for the dipole moment? So the dipole moment is basically represented by mu sign, and it is the product of the separation of the effective charges, that is whatever the electronegative difference between these two is, multiplied by the bond length of these two atoms, the bond length between these two atoms. This is the formula for the dipole moment. Okay, and of course no point of guessing, the SI unit for this would be, the unit for the charge is coulombic, and for the distance meter, so its unit is coulombic meter. but there is another famous unit that we normally use for this, that is called as dBi, which is named after a Dutch scientist, and 1 dBi is actually equivalent to 3.33564 into 10 raised power minus 30 coulombic meter. This will be useful if you get a numerical, but normally you will be given the dipole moment in terms of dBi. Alright, I hope everything is clear till now. Okay, so let's just do some kind of numerical, or sorry, some examples. First we will start with carbon dioxide, okay, or maybe BeCl2, both linear. We are starting with the linear molecules. So we know that the shape of the carbon dioxide is like this, right? Not exactly like this. We have already studied the Lewis structure, but we are not going to that thing. But always remember that it has a linear structure, right? So because of which what happen is oxygen is more electronegative. So we have a dipole moment towards this. Similarly towards the other oxygen also, but these dipole moment, one because of this CO, another because of this CO, they both are equal but they are in the opposite direction, because of which what will happen, they will cancel out each other and we will have dipole moment as 0. That is why carbon dioxide is not a polar molecule, rather it is non-polar molecule despite having a individual polar bond. CO itself is a polar bond, but overall dipole moment get cancelled out. Similarly for BeCl2, it also has a linear structure. So the chlorine definitely is more electronegative, so we do have the polar bond, but they are present exactly in the opposite direction with the same quantity, because of which they will cancel out, and this will also be showing 0 dipole moment. That means it is non-polar in nature. Something which doesn't have any kind of overall dipole moment, that will be considered as non-polar. Okay, that is one thing that you need to remember. Another thing is, you need to remember, if something is polar in nature, its solubility increases. So instead of asking for polar or non-polar nature, or mu is equals to 0 or not, they can also ask about the solubility. So we will do more example based on that later on, but let's just move some more examples. Secondly, what about water? So we know that water has a band structure. It's not linear. We have something like this. Reason being, oxygen, reason being, just a second, I draw it wrong. It's H2O rather than, yeah. So this is oxygen, hydrogen, hydrogen. So this oxygen has a lone pair of electron as well. That is why it is not going to have the band shape. So we have not studied about the shapes yet, that we are going to study in the subsequent approaches, but as of now just remember that the water doesn't have the linear structure. Now what happened here is, we do have the individual dipole moment because oxygen is more electronegative, but at the same time we have another dipole moment. When we have a lone pair of electron, that also have a kind of dipole moment, and we show it by showing the arrow towards the lone pair. So we have something like this. Okay, because of this, overall the dipole moment would not be equals to 0. In fact, to be precise, its dipole moment is 1.85 dBi. Okay, now let's just move to some other example. Let's say BF3. Okay, now the shape of BF3 is trigonal planar. Okay, what is the shape of trigonal planar? It's basically like this. each atom is present at 120 degree. Okay, so fluorine is definitely more electronegative, so we have individual dipole bond, but the resultant dipole moment in this case will also be equals to 0. Why? Because this is symmetrical in nature. Okay, anything which is symmetrical in nature, because of which what will happen, even if the individual bond has an individual dipole, still the overall dipole moment will get cancelled out. Okay, so in this case we will have dipole moment 0, that is, this is non-polar in nature. This is resultant dipole, which is equals to 0. So always remember, you have to just look for the symmetry. If the molecule is entirely symmetrical, that means it is not going to have a dipole moment. Another trick, if you have a kind of lone pair, then also it is going to have a dipole moment. Okay, another example we can take is maybe ammonia, NH3. Okay, so NH3 has a shape of trigonal pyramidal. Okay, why? Because nitrogen also has a lone pair. So it look like something like this. It has a lone pair, hydrogen, hydrogen and hydrogen. Okay, so I have already told you, when we have a lone pair, we show the dipole towards the arrow towards this, and of course out of hydrogen and nitrogen is more electronegative, so we are going to show the individual dipole like this. Okay, so from this figure itself it is obvious that it is not going to have the have a zero dipole moment. This will be a polar molecule, so in this case mu will be not equals to 0. In fact, the mu in this case is 4.90 into 10 raised to power minus 30 coulombic meter. Okay, another important question that arises most of the time is compare it with NF3. Now NF3 also have the same trigonal pyramidal shape. If we show it, same structure, but instead of hydrogen we have fluorine. But now if we compare nitrogen and fluorine, fluorine is more electronegative, so the direction for showing the dipole moment will change. But in this lone pair, it always shows towards the lone pair. So here you can see that they are actually in opposite direction. Okay, so in this case it will overall not be 0. Why? Because downward we have more dipole moment, but still the dipole moment of NF3 would be lesser than that of the NH3. Why? Because in NH3 every dipole point towards the same direction, whereas in this case it is pointing, the lone pair is pointing towards another direction and NF are pointing towards the another direction, and its mu is 0.80 10 raised to power minus 30 coulombic meter. Okay, I hope this is clear. Then another example that we can talk about is, most of these examples I am taking is they are symmetrical in nature. So wherever you see the symmetrical word, always remember the dipole would be 0. Let's say methane. So in this case it is having tetrahedral shape. It means hydrogen, 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 hydrogen. So they all are symmetrical in nature. Okay, it's difficult to show with the help of 2D dimension, but this is entirely symmetrical. And since this is symmetrical, mu in this case would be 0. Okay, whereas if I compare it with CH3Cl, in that case what will happen? We have Cl bond and then hydrogen, hydrogen, hydrogen. So in this particular case, though the shape remain the same, but in this particular case the dipole moment will not be equals to 0. Why? Because one of the bond has been changed. So it is not typically symmetrical in terms of dipole moment. Okay, so you should keep that thing also in mind. Then another example that we can talk about is PCl5 and SF6. PCl5, it is also totally symmetrical in nature. Its shape is trigonal bipyramidal. Okay, so it has shape like this. 3 chlorine bonds in one of the plane and rest of the 2 above the plane and below the plane. Okay, but this is also totally symmetrical in nature, so that is why mu will be 0 in this case as well. Okay, same goes for another popular molecule, SF6. This is also symmetrical in nature. Okay, so we have shape like this. Just a second. Four fluorine in the same plane and the rest 2 above the plane and below the plane. So in this case also this is totally symmetrical, that is why this will be non-polar in nature. Okay, I hope this is clear. And similarly we can also differentiate between the cis and trans, so but there are some more examples. I'll make a detailed video where we will discuss more of the exam related question, but as of now these examples are good enough to understand. Okay, another important question that I would like to discuss is which is majorly asked, or you should also know that you will be asked to arrange HCl, HF, HCl, HBr, HI in increasing order of dipole moment. Okay, this is one of the common question which can be asked. Okay, so you should always remember that dipole moment has a formula of mu. Dipole moment is being represented by mu is equals to q, that is the charge difference, effective charge difference multiplied by the distance between these atoms. Okay, so if we compare these molecule, hydrogen is common, so we just have to compare the electronegativity of the anion, that is fluorine, chlorine, bromine and iodine. So on the basis of charge, we know that electronegativity wise, fluorine has a highest electronegative, then chlorine, then bromine, then iodine, right, based on electronegativity. But based on distance, the bond length, it has been found that HI has a greater bond length than HBr, then HCl, then HF. Now in this particular case and in most of the case, when we have entirely opposite trend for both the factors on which dipole moment based, normally we have a dominating factor. Okay, so in this case the dominating factor is normally is the Q, the charge separation. Therefore, the dipole moment will vary in terms of HF, then HCl, then HBr, then HI. Okay, most of the cases, but there are exceptions also. So in the next few videos we will talk about those exceptions, but as of now just remember, if you have a trend where both the factors are working in the opposite direction, first pay attention to the electronegative, that is a charge separation. Okay, so I hope these videos, these examples were clear to you. If you have any other example or any other question in mind, you can comment down below. Okay, and in the next video we will talk about the Fezan's rule. Okay, thank you so much.